Okay, so rates of change and limits. So we're on page 59. And by the way, there is chapter 2 has 4 sections, I believe, 4 sections. So we will not be splitting this up. We're going to go all the way from 2.1, 2, 3, 4, and then take the test. Okay? All right, so 2.1, rates of change and limits. So the average and instantaneous speed. So let's say that what we are trying to find is y is equal to x squared. So at 1, you have 1 right here. Okay, so this is the point, okay? And what we're trying to find is the rate of change or the instantaneous rate of change at 1, okay? So far we have no idea how to find what is the instantaneous or at that exact moment of 1, what the rate of change is. Okay, all we know so far is know how to do the average speed. And average speed is what? Average speed is the difference in distance over the difference in time, right? Isn't this what speed is, right? So if it took me 2 hours to get to, I don't know, if it took me 2 hours to get to, where do you go for 2 hours? Medford, I guess, Medford. So if I do 120 miles in 2 hours, my average speed is going to be 60 miles an hour, right? 60 miles an hour. This would be how I would calculate my average speed, okay? But that doesn't mean that at any given moment of the time, I'm going to be traveling at 60 miles an hour. I do not know because my speed is not going to go from 0 hour to 2 hour, right? This is where I hit Medford, right? It's not going to go 60 miles straight as a line, right? You're going to go like this, like this, like this, and whatever, right? Okay, just the average speed was 60 miles an hour, okay? So again, we know how to find the average speed. The average speed is this. Average speed is the delta D over the delta T, okay? So let's see if we can do example number 1. Let's do example number 1. Okay, so before we go ahead, let me go ahead and let's go ahead and make sure we state this. This is the same as if I had an equation, if I had that this is equal to f of x, okay, this is going to be what? X plus t, and I'm going to subtract when t is equal to 0 over t. Okay, this is the same as that. Or as the book says, it says t plus h minus f of t. Okay, so it's the same thing. Okay. Right. Now let's see if we can go example number 1. A rock breaks loose from the top of a tall cliff. What is the average speed during the first 2 seconds of the fall? Okay, so this is a free fall equation, and we've done free fall before. So I'm going to start from here. I'm going to drop like that. And the height, we know that this is going to be equal to what? Negative 16t squared plus v naught t plus s naught, right? The free fall equation, where we're just dropping it, right? The v naught is going to be equal to 0 because there is no initial speed. I'm not throwing it down, I'm just dropping it, okay? And the initial height was whatever the initial height was. So if we call this height 0, okay, then this would also be 0 too. And this is what's going to be my height at any given time, which makes sense because if this is 0, it's going to be going in a negative direction, right? If we call this positive, if we call this side positive and this side negative, it's going to be going negative, right? Negative. So I do not know what the average, I don't know what the instantaneous speed at t equal 2 is, but I can calculate the average speed. The average speed is going to be what? It's going to be S sub 2 at time, how long it traveled at time 2 versus where it was to start, right? S of t equals 0. And I'm going to go from 2 minus 0, right? The time is 2 seconds versus the initial time was 0. So if I do this, I get minus 16 times t squared, right? Because it's t squared minus 16 times 0 squared over 2 minus 0. So that's 0, that's 0. So I'm going to get what? Negative 16 times 2 over 2. So this 2 cancels out. Negative 32 meters per second squared. Per second, right? Meters per second, right? That was the average speed during those 2 seconds. Okay? Oh, it's feet. I'm sorry. Not meters. Feet. How do I know that it's feet? Can anybody tell me how I know it's feet? This guy's your giveaway right here, right? This is what? Where did I get that from? 32 feet per second squared, the gravitational constant, right? So it must be in feet, right? Feet, okay? Okay, so that's instantaneous speed. Let's see if we can find the instantaneous speed. So the way we're gonna find the instantaneous speed is we're gonna go from 0, so we went from 2. So here we're gonna do 0 to 2, right? We went from 0 to 2, okay? And we're gonna take that time interval and make it smaller and smaller and smaller, okay? So I would do the same thing at 1 second, it would be what? It would be S sub 1 minus S sub 0 divided by 1 minus 0. If I wanted to find the time at S sub at 0.1 second, it's going to look like this. And I can continuously try to make that time interval smaller and smaller, right? So this would be not 1. Yeah, so 0.1, okay. So 0.0001 minus S sub 0 over 0.0001. I can do this, right? But if you looked at it, I had S sub t was going to be equal to negative 16t squared minus plus v naught t plus s naught. Now this was 0, so I ended up with negative 16t squared, right? So in here, what am I putting? I'm putting negative 16t squared here, right? So I'm going to put negative 16. So if I go ahead and make this t instead of just a time, it would be negative 16t squared minus, this is going to be 0 over the t, which is going to be equal to negative 16t, right? Okay, so let's go ahead and see if we can plot that. If you plot that, you go on page 60, right? On the left-hand side, there is a way to do that, right? Does anybody know where that 64 is coming from?
Is it 16 times 4?
16 times t squared, right? Which is what, because we're trying to find in the example, it says find the speed of the rock example at t is equal to 2. So when t is equal to 2, okay, what do we have? S of t 2 is equal to 16, 2 squared minus 0 minus, or plus 0 plus 0, right? Because this was v naught t and this was s naught, they're both 0, right? So I'm going to negative, this is where I get the 64 from. Okay, so this is where I'm starting at negative, this is S of t 2, right? So to find the instantaneous at 2, so this, we call this 2, if this is 2, I'm going to go from making my interval 1, okay, so it's going to be this guy and this guy here, and then I'm going to go ahead and I'm going to reduce that to 0, as close as I can get to 0. In other words, the delta t is going to be 0. I'm going to make that time interval as close to 0 as possible to find the instantaneous rate of change, okay? So in other words, I'm going to go S of t. If I make the interval 0.1, it's going to look like this, right? Because the delta t is the t at the second point, and this is the t at the starting point, right? And this would be the time, how much it traveled at 2.1 seconds, and where it started from. Okay, then I can go ahead and make this 0.1 and make it 0.1 like that. And I can continue to work that down. And that's exactly what they did on that left-hand table. Okay, so if you do that, let's go ahead and verify, 0.01, which is this guy right here. See if you can figure this out. So this guy here is going to be negative 16 times 2.01 squared minus negative 16 times 2 squared over 2.01 minus 2. Are you able to get 64.16 on your calculators? Did everybody get that? Nod your head, Natalie. Natalie, did you get it? Okay. Kaden? Okay, all right. So this is what it's going to look like. Okay, this is how you're going to find your instantaneous rate of change. Okay, so if you think about it, if you actually think about it graphically, so what actually is the instantaneous rate of change? What do you think is the actual rate of change? Where is it trying to converge to? What is the number that it's converging to?
64.
64, right? So you have empirically shown or numerically shown that the instantaneous rate of change for that equation at t equals time 2, when t is equal to 2, is 64, okay? So graphically what that means is that if I blow up that area right here, let me make it kind of dramatically draw. So this is 2, okay? And this was 0.1, so this is going to be 2.01, all right? The instantaneous rate of change, the average speed that you drew was from here to here. So it is actually the slope of this line, because this guy here is going to be the delta D. This guy here is going to be the delta T, right? Because this is the time difference. This is the change in the distance, okay? Now, as you pull this closer and closer and closer, the time closer and closer, what ends up happening is that you are looking at, it was from here to here, it's going to go to here, and it's going to go to here. It actually becomes the tangent line at that point. Can we see that? You guys see that? That's the tangent line at that point. Okay, so it's a line that's tangent right here, that abuts right up to the curve. Okay, so it's the tangent line. It is the slope of the tangent line is your instantaneous rate of change. Okay, and that's what they mean by when you look at the 64. Okay, definition of a limit. Okay, let's go ahead and look at the definition of a limit. Okay, so in here we are looking at the function f is equal to f of x is equal to sine x over x. If you draw the graph, if you look at if you do your calculator, your graph is going to look like this. Okay. So what is wrong with this graph? Can anybody tell me what's wrong with this graph? The graph that they show on A, I guess that is, figure 2.1a, left-hand side, bottom of the page. Does anybody know what's wrong with this?
Doesn't sine usually start at 0?
This is true. Yeah, that's true, but that's not what I'm looking for. What happens at x equals 0? What's the value of this graph?
It's 1.
It looks like it's 1.
It's something. It's something.
Why is it not 1?
Because it should be nothing. Or
0 should be an asymptote because you can't get rid of it from the denominator.
Here, x cannot be 0, correct? So not necessarily an asymptote, but what we're looking for is a open dot, right?
aha.
There's nothing there. You cannot have x equal to be 0. Okay, so again, the calculator is only as good as the user. Okay, so here we go. There is no value, so f of 0 is undefined, right? You do not have f equal to 0, right? However, if I were to continue, if I were to make t0, t, so this was what, 1? Was this 1? This is 2. So if this is 2, and I go here and I go closer, if x goes closer to 0 and 0, closer to 0 and 0, f of x is trying to go to 1, right? It never quite gets there because you cannot have 0 here. So the limit as x approaches 0 of sine x over x is actually 1. Okay, so as x approaches 0, it's going to try to get to 1. So the limit actually does exist. There is a limit, and it is 1. However, again, the value here is undefined. What if I approach it from the other side? Does that make a difference in the limit? Or does it still approach 1? What does it look like? It looks like it's going to approach 1, right? It's still going to approach 1, right? From here, it's still trying to go to 1. It's trying to go to 1, right? But it never really gets there. Okay? So let's go ahead and look at some of these interesting things. If I go to top of page 61, okay, the first one here is I have an open dot here at, this is what, x equals 1. So in this function here, which is actually what we're drawing is x squared minus 1 over x minus 1. If I draw this, what is my limit as x approaches 1? What does it try to become? It tries to become 2, correct? Although it can never get there because x cannot be 1. So the limit is 2. Okay. Now let's look at a different one. Let's look at the b. At b, actually it gives you a value here. Okay. So the limit is still 2. The limit is still 2 because as it gets closer and closer to 1, it's trying to go to 2. So the limit is still 2, but now f of 1 is defined as 1, it looks like. Okay, so f of 1 is 1. Okay? All right.
They're just trying to trick us.
Well, that's right. They're not doing, are they doing a good job at it? Now the last one is when you have actually a closed dot. and the function is actually truly x plus 1. Okay, the limit again is it's trying to get to 2, it's trying to get to 2, it's trying to get to 2, right? 2, and f of 1 is equal to 2 because there's a closed dot. It is actually 2 at this point because when x goes to 1, this becomes 1 plus 1, which is equal to 2. Okay? So let's look at some of the properties of limits, okay? So in the middle of page 61, there is a properties of limits. Properties of limits. So it's giving you two different functions there, f of x and g of x. And they're saying that the limit of f of x as x approaches c is equal to L, limit as x approaches c, g of x is equal to n, then the limit of x of c, when x approaches c, of f plus x plus g of x is equal to L plus m. Okay? In other words, this guy, this limits, this goes to L, this guy goes to M, so the combination, the addition is addition like that, right? Also, if I subtract it, you just subtract those. Okay, so plus or minus here. So that's the sum rule and the difference rule. The product rule is the same thing. So if I have this guy times this guy, and this is nothing more than L times M. Okay, I'm not even going to write the quotient rule. Constant multiple. In other words, if I have something that looks like this, and I have a constant up here that is K, this K can be pulled up front, and it looks like K limit as x approaches C, f of x is equal to, we already know this as being L, so it's K times L. That is the product rule. The constant multiple rule. If you flip the page, there's a power rule. The power rule is the same thing, nothing really interesting there. Okay, so this is kind of new for you guys. We're actually going to look and maneuver and try to work with these limits, okay? So let's see if we can actually solve a few of these and get a good feel for it. So example number 3, I have limit as x approaches c. I have x cubed plus 4x squared minus 3, where the limit as x approaches c so x approaches x, this is going to be equal to c. Okay, so this is what? This is the same as limit as x approaches c, x cubed plus limit as x approaches c, 4x squared minus limit as x approaches c, 3. This guy here using the power rule, since this guy is c, this is going to be c cubed. This guy here, I can pull the 4 out, 4c squared. And this guy here is nothing more than 3. I don't care what happens to x, it's just a number, so this is going to be 3. Okay. The second one, I have x to the 4th plus x squared minus 1, x squared plus 5. It's the same as limit x approaches c, x to the 4th plus x squared minus 1 over limit as x approaches c x squared plus 5, right? This was the quotient rule, okay? And this guy here is just as we did before, the one we did before. This ends up becoming c to the 4th plus c squared minus 1. The bottom becomes c squared plus 5, okay? And that's it. The polynomial and rational functions. Okay, go ahead and read that. Should be pretty simple. Okay, let's do example number 4. Example number 4. Using theorem 2, if I have limit as x approaches 3, and I'm trying to figure out x squared 2 minus x. So this just becomes 3 squared 2 minus 3, really, right? Minus 9, right? Because we're just replacing the x's with 3's, is all we're doing. Second one, we have limit as x approaches 2, x squared plus 2x plus 4x plus 2. Wherever x is, we just put 2 in there, and I get 2 squared, 2 times 2 plus 4 over 2 plus 2. 4, 4, and 4, that's 12. 4, 3. Okay. So let's go and do a little bit of trickeration. We'll do example number 5. Example number 5. Starting from example number 5, you can figure out, well, this might be a little harder than I thought it was. Because right now, you're not seeing anything that's really hard. As x goes to 0, tan x over x. Okay, what's going on here? So if I go limit as tan x over limit x as x approaches 0 on top and bottom, where does this go? Where does tangent x go as x goes to 0? This is tangent x, right? So as x goes to 0, this goes to 0. So this top's going to be 0. X goes to 0, this becomes 0 also. Now I have a 0 over 0. And it's definitely not a good thing, right? We don't like that. 0 over 0. Can't do that. Okay. So here comes over the tricky part. So what I'm going to do is I'm going to rewrite this as x goes to 0. Tan x is sine x over cosine x, 1 over x. Now, switch these guys over. I get this is limit as x goes to 0, sine x over x, 1 over cosine x. What happens to this? Where does cosine x go as x goes to 0?
One.
Goes to 1, right? So this guy is going to go to 1, right? Where does this guy go? We just learned this.
1.
1. Haha. 1 times 1 is equal to 1. Your answer is 1. Okay? So you see how what we were doing earlier makes no sense whatsoever, but this guy, woof, all of a sudden by changing this over here, I'm good to go. Okay? All right. So again, you have to kind of understand what's going on. You just have to try different things. Okay, last but not least, example number 6. Use a graph to explore whether this exists or not. So I have limit as x approaches 2. I have x cubed minus 1 over x minus 2. As x goes to 0, this becomes x goes to 2, this becomes 0. Okay, but I can't, there's no way that I can make any sense of this in terms of this. In other words, this one does not factor out to x minus 2, because if it did, they would cancel out and I would have nothing on the bottom and I'd be good, I'd be okay. But I don't have that because this is x cubed minus 1. So I'm just going to throw it into grapher, and if I look at the calculator, what does it show? It shows that at x equals 2, I have a vertical asymptote. I have a vertical asymptote, okay? So it's not gonna work. So I do not have a limit there, okay? Now, where am I at? Okay, so let's go ahead and stop right there, and then we'll do the one-sided and two-sided limits later on.